Welcome to problem solving session for Introduction to Group Theory. I am Siddhi Balu Ambore from IIT Gandhinagar, and today we will discuss problems related to syllabus from week 6. That is problems related to first isomorphism theorem, second isomorphism theorem, third isomorphism theorem, and some problems related to isometries of the plane. So let us start with our first question. Yeah, question 1. That if G is R plus, that is real numbers under addition, then which of the following is isomorphic to G mod Z as groups? And first option is X in C such that X power N is 1 for some N in Z, and B is X in C such that modulus of X is 2 under this set under multiplication, Cx in C such that mod X is 1 under multiplication, and D is G quotiented by Q. Okay, so I hope you all know what isomorphism is, right? We discussed this last time as well, but even now that if let G co and star B group, then P from G to G dash is called isomorphism, or not like this, but if we say G is isomorphic to G dash if there exists phi from G to G dash such that P is group homomorphism and P is bijection. We say that is P is bijective homomorphism. So phi is group homomorphism and phi is injective and surjective. So that's what isomorphic two groups being isomorphic mean. So here what they have given is that G is real numbers under addition, and now we have to see like what are all the groups are, I mean among these four, which are the groups that are isomorphic to G quotiented by Z. Okay, so any guesses for the from this option that which one is isomorphic to G quotiented by Z and which one is not? If it's not, then we have to give a reason, a valid reason, such that we can say that okay, this is not isomorphism. Or if we say that it is isomorphism or it is isomorphic to any of these sets, then we have to give a proper group homomorphism such that this holds. So any guesses why? So let us start with first one. What is your guess? Is first one Oh, this is also under multiplication, by the way. This is also under multiplication. Okay, someone said something in the chat. A. A is how can you give me a isomorphism? This is also under multiplication. Let me write this. Yeah. How can you say that it is isomorphic? So someone in the chat said that it is isomorphic to G quotiented by Z. So any so what is group isomorphism? If at all it is, then what is your group isomorphism from here to this set? Let us call this A. First of all, we know that this is a group. Okay, we proved this maybe last week or a week before that this is a group. Okay, this forms a group. We proved that. If you have a doubt that this, if you don't know whether this is group or not, so let me tell you that this is group. That x power n is equal to 1 for some n in Z. This forms group under multiplication in C. Okay, so what is your group homomorphism if this is a subgroup? Sorry, if this is isomorphism. Or if not, then give me some map from R to A such that its kernel will be my Z. So let us write this first isomorphism theorem here. Okay, so if first isomorphism, so let P from G to G dash be a group homomorphism. Let E be the subset of G that is mapped to the identity of G dash, that is E is contained in kernel of kernel of P. Then this E is normal in G and G quotiented by E is isomorphic to D dash. And this, for this, not G dash, I mean, it is isomorphic to image of P. And when we say that if my P is surjective group homomorphism, then this G quotiented by E is isomorphic to image, not image, then it becomes a complete G dash here. Okay, so this is what we have. So if you give me a map from G to A such that its kernel is Z, then we can say that this G quotiented by Z is isomorphic to this A. But can you give me a map, this map? Can we have such map? Mhm. First of all, when we have isomorphism, understand that they essentially become same group. Okay, so when we say that something is isomorphic, I mean, two groups are isomorphic, they kind of become identical. They have similar kind of elements. If, I mean, similar kind of subgroups, order of elements become same, and so on. So they are, it is like saying they are same group represented differently, something like that. So can we say that this R quotient G quotiented by Z or R quotiented by Z is isomorphic to this A? I mean, do we have like, note that here in this set A, this set A here, every element is of finite order if you observe properly. Can you see that? That every element in A is of finite order. Because if I take any x in this A, this x power n is 1 for some n, right? And even for product and so on. This forms a group, and each and every element here is such that its order is finite in C. Okay, but if you take this group, so in A, okay, so this is what I mean by A, okay? This A, in A, every element is of finite order. Everyone agrees to this, that every element in A is of finite order. Okay, and do we have that same property here in G quotiented by Z? Is every element in G quotient Z is of finite order? Can you give me one example? Or do you think that every element in G quotient Z is finite order? Now, my question is every element in G quotient Z, let me write this, R quotient Z just to, is of finite order? Can you, is this true? If this is true, then, I mean, we can then proceed and try to find isomorphism and so on. But is this true? Because no, because see, if I have every element here, because if there exists some isomorphism P from this G quotiented by Z to A, then A will go to some B here, right? And then A power n is 1. This will imply, I mean, A power n will be 0 here. If A power n is 0 here, I mean, that is NA, under addition we are writing, then this B power n must be 1, right? Here the group is under addition, here the group is under multiplication. Okay, so this B power n must be 1. But since we are talking about group isomorphisms, if I have even a one element in B which does not have finite order, then for that element to be here, I also need to have some A such that it will have infinite order or something of that sort. Because then in that, because E always goes to E here. So if there exists some element B here such that B power n is not equal to 1 for any n, then the A which I am mapping this B to, okay, must also have that kind of property, that A power n must not be equal to E for all, or 0 for all n in n. Because then NA, if it is it becomes 0, then this B power n must become 1. But that won't happen because 0 always goes to identity. Identity always goes to identity under group homomorphism. So can we have an element here? At least if we produce one element which does not have finite order in R mod Z, then we are done. So can you give me one element which does not have finite order in R quotient Z? Okay, so let me give you this element, root 2 plus Z. Does this have finite order? Order of this is what? This element belongs to R quotient Z, right? Root 2 belongs to R. Then this very well belongs to, okay, what is order of this? So root 2 belongs to R. So root 2 plus Z belongs to this R quotient by Z, right? And what is order of this element? If, suppose, if order of this root 2 plus Z is some K, then K times root 2 plus Z will be 0 bar, right? Here, 0 bar means 0 plus Z, that is essentially Z. So what does this imply? That K root 2 is plus Z is Z. This implies what? This K root 2 belongs to Z. Is this possible? And K is greater than equal to 1, okay? Is this possible for any K? It's not possible, okay? This is not possible because root 2 is a rational number. So doesn't matter how many times we, for any given integer k into this root 2 can never belong to Z. Okay, so is this okay? Like why this is not true? So this is definitely not a subgroup. This is definitely not a group which is isomorphic to G mod Z. So using this same argument, because this element here, if I want to send something here in A, which who has this pre-image root 2 plus Z, I don't have such element of infinite order in A because every element in A is of finite order and so on. Okay. You can also check for this. If this is not something, then try to do this. This be from A comma plus 2 G mod Z. Try to produce some, doesn't matter. It's not possible because this has elements of infinite order and this does not have element of infinite order. Every element is of finite order. Is this okay? Any doubts, please let me know. Otherwise, I will move to next part. Okay, if not, then let us move to next part then. Now B. B is okay. So first of all, B is this group. Sorry, not group. B is this set such that mod X is 2 under multiplication. Is this group first of all? Is this even a group? Mod X is equal to 2. Is this group? Okay, if you remember properly, note that this is not a group. Let me just write this. This is not a group. If I call this B, note that B is not a group. Can one give me and why this is not a group? B is not closed under multiplication, okay? Because X is equal to 2 belongs to B. So because but X into X, that is 4 and mod 4 is 4 and this mod is not the real mod, okay? This is if my X is A plus BI, then mod X is this thing, A square plus B square, okay? So 4. So this is not closed under multiplication. So the B which is given here is not uh, closed under multiplication. So this is not a group. So we don't have to worry about this B being isomorphic to G quotient Z as a subgroup. Now the third part. C is again under multiplication. So now this C is all those X in C such that mod X is equal to 1 under multiplication. Do you think this will give me the required group which is isomorphic to G quotient Z? So what do you think? Can we produce phi from R to this, let us call this C, such that kernel of this phi is my Z? Any guesses? So we can have this x going to e power 2 pi ix. Okay, and then this is what? This is actually x going to cos 2 pi x plus I sine 2 pi x. Okay, and mod of this thing is, what is mod of this? Mod of p of x is, or this is cos square 2 pi x plus sine square 2 pi x square modulus, and this is 1. Okay, so this belongs to my set C. Okay, and you can also see that the converse is also true. Every element of this set is of this form, some cos theta, comma sine theta. You can check this. Okay, try to prove that these two are actually equal. And when I write this actually means this cos theta plus I sine theta. This theta belongs to I. You can check this. Okay, so with this phi is here, R going to C and X, so not C, this C, and it is e 2 pi ix, or let me just write this cos 2 pi x plus I sine 2 pi x. And what is kernel of this map now? So kernel of this phi is all those x in R such that p of x is 0. Sorry, phi of x is 1. Okay, we are in multiple. So we are going from 0 to multiplicative steps, from addition group to multiplicative group. So here it is 1. So that is x in R such that cos 2 pi x plus I sine 2 pi x is equal to 1. So this imply all those x in R. I want this to be equal. So here we do not have any imaginary part. So what I need is that cos 2 pi x needs to be 1 and sine 2 pi x needs to be 0. So what will be the x then? It will be all integers, right? Because for non-integers, we know that cos is 1 for even multiples of pi, and sine is 0 for even multiples of pi. And here I already have 2. Okay, I mean, sine is 0 even for odd multiples of pi. That's not a problem. But here for cos, we need to take care that it's 1 when even multiple of pi and -1 when odd multiple of pi. So, but anyway, we have 2 here. So it becomes So that's why X is in R such that X belongs to Z. So this becomes my Z. Okay, so this is P which we obtain, and from now I have phi, and this is onto, you can check. So that's what I said here, that please check that these two sets are equal and I can obtain such theta from R. Okay, and then this phi from then R to C is onto group, or onto means surjective group isomorphism, and we just showed that this kernel of phi is Z. We just showed this kernel of phi is Z, and therefore by first isomorphism theorem, this R quotiented by Z is isomorphic to C, that is this X in C such that mod X is 1 under multiplication. Let me write this under multiplication. So is this okay? We used first isomorphism theorem to obtain this. So this C is actually the group which we need, which is isomorphic to G quotiented by my Z. Any doubts here? The only part which needs to be checked, that this is onto map. And this is true. This is actually is equal to S1 if you know what S1 is. This unit circle in R2. If I look at C in R2, this is what it represents. Okay. This C. When I say C, not the complex, the set C here. And now the fourth one. Fourth is not the D part. My G they have given is, let me call this D. D is G quotiented by Q. Is this isomorphic to my G quotiented by Z? I mean, is this true? We have to check. So to check, we have to check whether this is true. And what is your guess? Is is this true? I mean, here see. Is this true first of all? I mean, or what is your guess? If it's true, if it's not, and if not, then why not? What's the problem for this? Any guesses? First of all, is this true or false? What is your guess? Whether it's true or false? Just give me that guess, then we can proceed accordingly. Okay, so for this is again, this is not true. Okay, I mean this, that is, let me write. G quotiented by Q is not isomorphic to G quotiented by Z. The reason being, note that here in G quotiented by Z, there are elements, there are non-zero elements which has finite order. For example, let m by n plus m by n belongs to R, then m by n plus Z belongs to this G D quotiented by Z, right? And then this non-zero, not non-zero. to say this. Latest only thing I need is that n greater than 1. That's it. I don't, and m non-zero. Let this be non-zero and n greater than 1. Then this belongs here. Okay, and just let m comma n belongs to z such that GCD m comma n is 1, m n non-zero, and m quotiented by n belongs to R implies non-zero m quotiented by n belongs to G quotiented by z. For this to be non-zero in G quotiented by z, I needed this. The GCD of m and n is 1. Okay, and I'm assuming that this n is greater than 1. Belongs to what? G quotiented by z. Okay, this is there. And this element has order n, right? N m by n plus z is 0 bar. You can check because since n m by n is m, which belongs to z, and that's why this becomes 0 in G quotiented by z. So I have element of finite order in G quotiented by z. Therefore, there exists, or if you want, 2 by 3. Order of, okay, 2 by 3 plus z, order of 2 by 3 is 3. Okay, that's it. We got one explicit example. So there exists elements in G quotiented by z of finite order. So do we have elements of finite order in G quotiented by Q? Do we have this? Is this possible? Do we have elements of finite order in G quotient Q? So if some non-zero x belongs to R such that non-zero x, x need not be x, we do not need x to be in Q for this belongs to G quotiented by Q. So does this what will be the order of x plus Q? What will be order of x plus Q? Can this ever be finite? Can this ever be finite? Because if order of x plus Q is some k, then k into x plus Q will be 0 bar. So, or Q, is Q. So this will imply this kx belongs to Q, right? So I have this x not in Q, but kx belongs to Q. Is this possible? See, kx belongs to Q and k belongs to Q, right? So this will imply 1 by k also belongs to Q. So 1 by k into k x will also belongs to Q. This implies that x belongs to Q, but this contradicts my choice of x itself. So this is not true. Okay, so no element in G, except for the identity, no non-identity element in G quotient Q has finite order. Okay, every element in G quotient Q has infinite order. But in G quotient Z, we have infinitely many elements which has a finite order. For example, take 1 by p. Okay, p, there are infinitely many prime numbers. So I have infinitely many elements of finite order. Okay, 1 by p will have order p. Or forget about prime numbers. 1 by n will have order n. That's it. And in G quotient Z. But every non-zero element in G quotient Q has infinitely many infinite order because of this. Okay, infinite order means for any n, this nx can never be in my set Q. Okay, is this clear? So therefore, no non-identity element in G quotient Q has finite order. Okay, so therefore G quotient Z is not isomorphic to G quotient Q. Okay, so the only group which is isomorphic to this G, not the only group, but out of this four, this was the only group which is isomorphic to my group G quotient Z. Any problem here? Any doubts? If not, then no doubts. Okay, great. So if not, then we will move to next question, and it is question 2. It says that let G be a finite group and T belongs to ort G. So ort G means set of automorphism. So it is bijective group homomorphisms from G to G. Okay, such that Tx is X for X in G, if and only if X is equal to E. And then true or false that for all G in G, there exists X in G such that G is equal to X inverse Tx. This is what they have asked. So we are given that G is finite group, T is automorphism on G such that Tx is X. If Tx is X for some X in G, then that X must be E. And sorry, then we have to prove that, or we have to check whether for every given G, does there exist some X such that this G is X inverse Tx for this T. So is this true? Or false? What is your can you start from somewhere? Okay, so this statement is true, and we can first note that G is finite group, given that G is a finite group. Okay, and T is such that, so we define this map G to G such that X is now going to X inverse Tx. Okay, and what we will do is we have to show that this G, for every G, there exists some X such that this G is X inverse Tx. So this is what we will do. We will define map of this kind, which has this structure, and then we will try to show that this is isomorphism. And once I have isomorphism, I will have this one-to-one correspondence from element of G to this element of G, but they will be of this form, X inverse Tx. Okay, so what we will do is we will try to show that this is surjective map, and since G is finite, we will get that this will also be a bijective map because we have surjective group homomorphism on a finite group, then it will be isomorphism as well, and then we will get the required result. Okay, so how to prove that this is surjective? Or we can also start with proving that this is injective, whatever suits you. So since we'll try to prove that let A comma B belongs to G such that P of A is equal to phi of B. So this will imply what? Phi of A is what? A inverse TA, right? This is B inverse TB. So this will imply what? T of A, T of B inverse is equal to A B inverse, right? But T is group automorphism. So this will give me T of A, T of B inverse is equal to AB inverse. So this is T of AB inverse is equal to AB inverse. So this is what I have. T of AB inverse is equal to AB inverse. But from given property of T, if T of X is equal to X for some X in G, then that X is E. So this will imply what? From the given property or given hypothesis on given condition on T, this AB inverse, we get AB inverse as E, right? But this will imply what? A will be equal to B then, right? AB inverse is B, then multiply by B both sides. This will imply AB inverse B will be EB and A will be equal to AB. So therefore, what I get that phi of A is equal to phi of B implies A equals to B. Therefore, I get that phi is injective map. And as I mentioned earlier, since phi is injective, and G is finite group, we get that P is also an onto map. Is this okay? Is there any problem here? So we wanted expression of this kind, x inverse tx. So we defined this map free from x to x inverse, which sends x to x inverse tx. And we proved that this T is injective map. And since G is a finite group, this T will also be an onto map. Okay, this I hope you understand. T injective and G is finite, so phi is also an I2 map, onto map. Okay, so therefore we get that phi is isomorphism from whatever we have obtained so far. Okay, so once I have this, that phi is an isomorphism, this will imply what? Or we do not even need isomorphism, since so therefore phi is an isomorphism. Therefore, for every G in G, there exists, I mean, therefore phi is onto, and once I have this ontoness, for all G in G, then there exists X in G such that P of X is G. So when I have this implies that X inverse T of X is G. The ontoness of this map will give me this expression. I mean, this is also in isomorphism, as I mentioned earlier. So phi was injective, and because of finite order of G, I get that phi is onto. And since phi is onto, if I write this G and G dash or G dash G, so I mean, anyway, G dash will also be equal to G. Okay, so for every element here, I get some X in G dash. I'm just expressing both domain and codomain differently to understand the difference. That if I choose some G in G, it implies there exists some X in G dash, such that this phi of X will be my G. But what is phi of X? It is X inverse Tx. So for every G, I'm getting some X, and which is precisely pre-image of this map under this phi, such that this X inverse Tx will be my G. The ontoness is actually giving me that I can express every G as X inverse Tx. And I obtained, I mean, I could have this injectivity of a map because of this condition, that whenever I have Tx is equal to X, then my X is E. We use that property here in order to prove my phi is injective map. Okay, so this property is important, then only we can say this. And so what this gives me is that G is a finite group and T is automorphism, such that Tx is X if and only if my X is identity. Then using this T, I can express every element of that group G as X inverse Tx. Okay, and now any doubts here? Any doubts? How things are happening, or any doubt, anything? If not, then we will move to this next question. It is related to this previous one. Just okay, yeah. So let sorry, not A. So let G be a finite group and let T belongs to or to G uh, be such that again this same thing if T of G is G, if and only if G is E. And now the condition is different here, that T square is identity map on G, then which of the following is correct? We have to check this. And first option is that G is abelian, B that G is cyclic, C G is not abelian, and D is like none of this is true. We can't conclude anything if about G if this property holds. That G is again finite group, T is an automorphism such that T of G is G if and only if my G is identity. And now there is one more condition here, that now T square is my identity map. So T, when I compose twice, I get the identity map. Now they are asking what can we say about G in this case. So from a previous example itself, we already have that. Any guesses what we can say about G being abelian, non-abelian, cyclic, or anything? A, G will be abelian. Okay, G will be abelian. Otherwise, uh, I mean, we'll prove that G will be abelian, and that's it. We can only conclude that about G in this case. And let us, so we have this information that using what it was question 2, I guess, using question 2, if some G is in G, then this G we can express as X inverse Tx, right? It requires only this property that G is finite and Tg is G if and only if G is C. And it satisfies the hypothesis of problem second. So we get that every element G in my group G can be expressed as for some X in G, can be expressed as X inverse Tx for some X in C. So we have that T of G is T of X inverse Tx, that is T of X inverse T of Tx, right? T is my group homomorphism. So this happens. So this imply my T of X inverse is there as it is, but T of it this is my T square X, and we are given that T square is identity. So since T square is identity map, I get that T of G is what? T of G is T of X inverse X, because T square X X. So this implies that T of G is T of X inverse X. And what can we say about what can we say about this now? Any cases here? So what can we say about this now? So now my T of G is still T of X inverse, right? So this is T of X inverse, if you check, and this is X, right? Since T is in odd G. And so if I modify this a bit, T of X inverse, and this is X inverse inverse, right? So then I get this. This is X inverse, wait, T of X whole inverse, right? But X inverse T of X was what? G. So this is G inverse. So therefore, my T is like this. T of G is G inverse for all G in G. So we now, using all the information which we have so far, we obtained this, that T of G is a G inverse. That's it. And what can we say after this about G? So since T is like this, so for all A comma B in G, T of AB is equal to T of A, T of B, right? And this is what? A inverse, B inverse. Okay, but also T of AB is what? By definition, it is AB inverse. So this is B inverse, A inverse. Okay, so therefore, what I get is that A inverse B inverse is equal to B inverse A inverse. And if you do proper shuffling, you get that AB, or just write this as BA inverse is equal to AB inverse. And this imply that my AB is equal to BA. Okay? Any doubts here? So from this, we obtained that G is a abelian group. Okay? So this one is anyway false. So any doubts here? Okay. Assume there are no doubts. If there are any doubts, please let me know. Okay, and from the information given here, we can only conclude about G being abelian. Okay, we do not know anything about G being cyclic, because generators of G could be anything. And if you want, we can try to obtain some explicit example of finite group G. Uh, such that G need not be cyclic, but all these conditions hold. Okay, if you find such example, uh, please let us all know. Okay, so this you can check like obtain. This I'm leaving as an exercise. Obtain counter example, not counter example. I mean, obtain some non-cyclic group G such that T is, I mean, G has all these properties, and but G is not cyclic. So I need to start with an abelian group, uh, and which has all these properties, and it is not cyclic. So obtain an example of non-cyclic group satisfying of these properties. Okay, this is not true. Okay, and this is anyway not true. If you want, we can discuss this next week. I mean, at the moment, I do not have any counter example, but we can try it. If anyone has any counter example, please let us know. Okay, so what we have to do is we have to find a group G such that if T is automorphism such that if T G is equal to G, if and only if G is E, this kind of T's we need in automorphism group of G. And we want T square to be identity map, and we have to check what we can conclude about G. Okay, and try to find just an abelian group. Try to find a non-cyclic group in short. Okay. Any doubts? If you find any counterexample of this, please put this in the discussion forum. Otherwise, we will try to find some counterexample. Okay, any doubts here? If not, then we will move to next question. This one is okay. So let A and B be two groups and C be a normal subgroup of A and D be a normal subgroup of B, then which of the following are correct? We have to check this. A part that C cross D is a normal subgroup of A cross B. B that A cross B quotient C cross EB. So this is identity in B. This they're asking whether this is isomorphic to A quotient EB. Okay, so meanwhile, please try to obtain some counterexamples or try to think of the proof for the statements which you feel are false or true. This one and fourth one is all of the above. So which one of these do you think are true and which one are false? So A and B are two groups, and C is a normal subgroup of A and D is a normal subgroup of B, and we have to prove, disprove, give counterexample of these statements. The first one, do you think that C cross D is a normal subgroup of A cross B? Any cases here? Is this true or false? We have to prove that C cross D is a normal subgroup of A cross B. So what we need to do, that for all G in A cross B, no, yeah, for all H in C cross D and for all G in A cross B, what we need to check? GHG inverse, whether this belongs to C cross D or not. So if I say any H belongs here in C cross D, it is of this form, right? H is equal to C comma D. And if I take any G in A cross B, it is some A comma B. And then G inverse, by definition of this product, it is A inverse B inverse. Okay, I mean, I hope you all know this. That's how it works in product of groups. Okay, so we have to check this. GHG inverse is what? This is AB, A comma B, C comma D into A inverse, B inverse. And from the way the multiplication is defined in products, we have this CA inverse, DB inverse, and further we have this CA inverse, BDB inverse. And now we have to check whether this belongs to my C cross D or not. So does this belong to C cross D? So what we need to check? We need to check whether this ACA inverse belongs to C and whether this BDB inverse belongs to D or not. And is this true? Note that. Note that C belongs to C and A belongs to A, and C is normal subgroup of A. So therefore, by the normality of C in A, I get that this ACA inverse belongs to A. Okay, and similarly, my D belongs to D and B belongs to A. Sorry, B belongs to B, and D is normal subgroup of B. So therefore, this BD, B inverse, this also belongs to, sorry, this belongs to C and this belongs to D. Okay, so this element here, therefore GHG inverse, that is ACA inverse, BDB inverse, this belongs to C cross D because each of the coordinate belong to. So ACA inverse belongs to C, D inverse belongs to D. Therefore, this is my H actually here. So therefore, C cross D is normal subgroup of A cross B. Any doubts here? this was straightforward. It does not ask for anything. We just wanted to check whether component wise every element land in the corresponding subgroup or not. Okay, and now B part. B is what? Yeah. A cross B, we are taking this C cross EB, whether this isomorphic to A cross EA cross B cross D. How can you do this? I mean, how to proceed with this? Do you think this is true? So before going to the B part, let us check for this one, because this will help us. This will help us in proving or disproving or obtaining counterexample of the previous part. So let us check the C part first. What do you think of this one? This is true or false? Or what is your guess for this C part? And if we think that this is true, then how to proceed with proving this? So this statement is true. Okay, and we have to prove this. To prove this A cross B quotiented by C cross D is isomorphic to A cross C, B cross D. See, and now this makes sense, okay, here, this A cross B quotient C cross D, because we just proved that from A part that this C cross D is actually a normal subgroup of my A cross B. So this, when we are writing here, this makes sense. So let me just mention this here. This is well defined as C cross D is normal subgroup of A cross B by part 1 by A. Okay, so that's why this makes sense. Now we need to prove this. How to proceed with this? So sorry. We will define this map from A cross B to this A quotient C cross B quotient D, such that A comma B is going to A plus C comma B plus D. Okay, any doubts here? This map is well defined, okay, because P of A1 B1 A2 B2, I mean, this map is well defined. You can check this, and also group homomorphism and everything. Anyone has any doubt about this map being group homomorphism? Okay, so check that P is group homomorphism. Okay. So what we will do is, our aim is that we will show that we want P is surjective and kernel of P to be C cross D. Okay, but is this map surjective? So any element of this is of the form this, right? A plus C comma B plus D, where A comma B belongs to A cross B, right? Then we can choose A in A and B in B, uh, and we will get that phi of A comma B will be definitely this A plus C comma B plus D, right? So for any element in this product, we have obtained an element in A cross B such that, yeah, such that its image is what we started with. So therefore, P is surjective homomorphism. Okay, so therefore by first isomorphism theorem, this A quotient P will be isomorphic to this. Okay, so what we need to do is now to show that kernel of P is C cross D. This is what we need to show here. And is this true? What is kernel of P? Kernel of P is all those A comma B in A cross B such that P of A comma B is identity. And what is identity there? It is AB in A cross B such that P of A comma B is what? It's just C cross D. That's what it means in quotient, right? It is C plus D. I mean in quotient, first one, or let me write this, is 0 bar comma 0 bar. Just 0 bar C, 0 bar D, and this all those AB in A cross B such that this will be what? This is A plus C comma B plus D. I want this to be equal to 0 bar C, 0 bar D, and this will imply what? A plus C is 0 bar and B plus D is 0 bar. And this is true only when this A belongs to C and B belongs to D. From the definition itself of the quotients. So this becomes what? Just A comma B in AB, and A is in A, C is in C. So this is just A comma B in C cross D. So this is just C cross D. Okay, so is this okay? So my kernel, I just proved that it is equal to C cross D. So therefore, from if I call this star, therefore from star I get this A cross B quotiented by C cross D is isomorphic to A cross C quotient this. Is this okay? Any doubts here? I mean, this was straightforward. Just we just had to uh, check whether this is. I mean, we just proved this properly that this is actually equal to this statement. So now we will now go back to our B. What do you think now? That whether this B is true or not. This B which we have here, what can we say about this B? So first of all, understand that the moment I have the previous result and C is anyway normal in A, which is given, and EB is always, I mean, the identity is always normal subgroup of any group. So this imply what? So this is equal to A cross C cross B cross EB, right? From previous statement. This is equal to this. This is isomorphic to this. So what we need to check is that whether this is isomorphic by option C above. So what we need to check is that whether this is true. Now we have to check this. We are now getting this. Now, can we say anything about these groups here? Is this always true? Now forget about the original statement which we had of this type. Using C part, we got from here to here, and now we have to check whether this is true or not. What is your guess in this case now? Whether this is true? There is no information given about A and B. A and B could be any groups which you want. Okay, and B and D, C and D are just given that they are normal subgroups of A and B. And they do not even have any restriction that C and D are proper, not proper, and whatever. They do not have any restriction on C and D as well. So can you think of any counterexamples where this won't hold? Okay, if not, then let us do this. Let A be our Z plus and B be Z plus. Okay, these are abelian groups. Every subgroup is finite subgroup. Sorry, every subgroup is normal subgroup. Okay, except for the trivial one, no subgroup of this is finite. Yeah, but A, B, both are groups, abelian group. So every subgroup is a normal subgroup. Okay. And so can you come up with some C and D such that this will hold here or does not hold here? So let P be MZ, right? Every subgroup looks like this and D be NZ, right? And we take this M not equal to N. And let us say that M and N both are positive. Okay, then what will this be? A quotiented by Z quotiented by MZ tensor this, sorry, not tensor, cross this Z. What is EB? EB might just 0 here, right? 0 isomorphic to Z quotiented by 0 cross this. Now I'm taking this. Okay, these are subgroups. This is my NZ. And this is what Z quotiented by, and this is just Z here if you observe properly. And isomorphic to Z cross Z quotient NZ. And what can you say about this? Can this be isomorphic? Can this ever be isomorphic? For n not equal to n. And even to make life easier, we can do also this. What can you say in this case? Can this groups will be isomorphic? First of all, these are well-defined groups, okay? Everything, we are in abelian and we are taking quotient with subgroups. So every subgroup is normal and this is well-defined. So can this happen? So here, if I take this element, 1 bar comma 0 bar, what is order of this element here? This will be m, okay? And here, order of 0 bar comma 1 bar will be n, okay? And if I have m strictly less than n, then can n have any element? So if in group isomorphism, if I have some element in G of order k, then there exists element of order k in my other group. So if I say G isomorphic to G dash, so if G has some element of order k, then G dash must also have some element of that order, because we are talking about bijection. So if something power becomes identity, then that same power must become identity here. If it does not become identity at that point, uh, uh, I mean, if my a power n is identity here, but b power n is not identity here, uh, then that would create a problem, because here a power n is identity, then p of a power n must also be identity here. And if that's not that will contradict the property of p being isomorphism. And secondly, if I have some element here such b here such that b power n is my identity, and this phi inverse of b, if this does not become identity for this same n, then this will again create a problem about phi being isomorphic, because in that case this b, this phi inverse b power n non-identity is mapping to this identity, and so this will belong to kernel of my map phi, and this will contradict the injectivity of my phi. Then I will have some non-zero kernel of my map phi. Oh, I hope you understand what I'm trying to say here. So for every element of order k, if my G is isomorphic to G dash, then G dash must have element of that same order. But here, Since m is strictly less than n and this group here has element of order m, then we must also have some element of order m here, but we do not have that here, right? Because here anyway we do not have any element. Every element here is of infinite order except for 0. And here every element has order n or some. I mean, it could also have some element of order m. Let us take primes. M and n won't work here. P and Q, P comma Q primes, and P not equal to Q. See, I mean, the earlier M and N won't help because let me keep M and N here. M and N primes, M not equal to N. Because we can have something like Z mod 2Z. GCD was 1, but still. Let us take primes and life will be easier. So if P less than Q, this M less than N, M and N are prime. So every element in Z mod NZ has order P or 0. Similarly in N or 0, and similarly in Z mod MZ, every element will have order M or 0. And since M not equal to N, it will create problem. Is this understandable what I'm trying to say here? Or let me just switch to P and Q. That actually helps. Okay, P, Q, Q, P, and so on. Okay, so I hope this helps. Every element, see here, we're taking power P. Will give me 0, but here that won't be the case. Adding it P times won't give me 0 because order of elements here is in the second coordinate is either Q or 0. Is this understandable? Is there any doubt here? And if this is difficult to understand, please, this is anyway isomorphic to Z mod QZ cross Z. Okay, this we proved last time. If A, this is true, we proved this last time, if you remember, and we also proved this for this one. ACB and so on. All the three combinations. So if you have problem understanding it this way, switch and check. This is not true. This statement is not true. This is not true. Or okay. And if you do not even want to go to some non-trivial example, understand that I can take any group G, let A and B be groups such that A is not isomorphic to B. Okay, we can take these two groups and then A quotiented by, and note that EA and A are normal subgroups, and here also EB and B are normal subgroups. For any group, a trivial group, and the group itself is normal in itself. So I can take this simply. A quotiented by A cross B quotiented by EB, and here A quotiented by EA cross B quotiented by B. And this is what? This is EA quotient B isomorphic to this A EB. And since A not isomorphic to B, and this you can see this is isomorphic to A, this is isomorphic to B, but A is not isomorphic to B. You can check this. We are going for checking whether A is isomorphic to B or not. So these are also trivial example. This is like completely trivial example where you do not need to understand anything about the structure of A and actual structures of A and B. Okay, and you can just say that this is not true here. This is not true. So this is not correct. This one is correct. We proved. And this. Please understand this properly. If you have any doubt, please ask. Any doubts here? Again, I'm asking you whether you still have any doubts for this. You understood the order argument which I gave here, right? How in the first coordinate the order element of order P are there, but here no element of order P is there. Understand that. And here also this is very trivial. This you, if you do not know how, I mean, you have to check this. I mean, this is not difficult, but, and you do not need to even check this, but please understand this. Okay? In order to prove this, you can just do this group isomorphism from here to here such that A comma EB going to AEB. This is just A here. Sorry, not EA. And this will be my A just. EB going to, I mean, you can just check here. And this will give me my group isomorphism from here to here. It won't matter. Take whatever element here you want, and this will, I mean, any identity, and this will still hold. Okay, similarly for B, you can do this and prove that this is isomorphism. Any doubts, please let me know. Otherwise, I will move to next question. Any doubts? If not, then let us move to next question. Let G be a group and H G is called characteristic subgroup if f of H is contained in H for all f in out of G. Then we have these statements. Then which of the following is our true? Okay, we will see how many statements we can prove or discuss. So note that every normal subgroup of G is a characteristic subgroup of G. Be that ZG is a characteristic subgroup of G. See that if G is a cyclic subgroup of G if G is a cyclic and then every subgroup of G is a characteristic subgroup of G, and D, that every characteristic subgroup of G is a normal subgroup of G. Okay, so any what again? Yeah, any guesses here? Which one is true? Do you think that every normal subgroup? So I hope you understood what is the definition of characteristic subgroup. So G is a group and H we start with any subgroup of G, and we have the automorphisms of G, and so H is such that under all automorphisms its image will again land back in my group H itself. Then we call it as a characteristic subgroup of my group G. Okay, so this is what we are asked, that every normal subgroup of G is a characteristic subgroup of G. Do you think that this is true? And if this is happening, then okay, so first statement, let me just copy paste it. Do you think this is true that every characteristic subgroup of G every normal subgroup of G is always a characteristic subgroup of G? Oops. So what we need to do in order to prove or disprove this? So in order to prove this, we have to prove it full-fledged, that we have to start with any group G, take any automorphism, and we have to show that if we have a normal subgroup, then its image will again land in that same subgroup. If you want to give a counter example, just give me one automorphism, a group G, and its normal subgroup, such that under that automorphism, my um image of that element under that automorphism does not land in that group, in that subgroup. So can you? So let me just, since we do not have much time left, understand that this statement is false. Okay, so can you give me a counter example of this statement? Just give me a group automorphism and element, a subgroup which is normal subgroup, but image is not landing in that subgroup. Okay, so we'll start with the simple group. This is not true. So we will start with this K for A, B, and AB. That is my C. Okay, this is abelian group. Therefore, every subgroup is a normal subgroup. Is this okay? can we define this T from K4 to K4 such that E is going to E, that's there. A is going to my B, B is going to A, and now C will go to C. Because see, this is well defined. This is well defined because see, AB phi of T of AB is what? T of C, which I'm defining as C. T of AB is T of A, T of B, which is AB, that is C, and that's what I have defined here. This is my T of C. So this is well defined. And T of A square is B square. This is identity. T of B square is A square, that is identity, and so on. You can check that this is well defined. So T is well defined group homomorphism, isomorphism, and automorphism. Okay, so T satisfies all the properties. So can you give me one? So we can take H to be this E comma A is normal because we are in abelian group. But what is phi of H? It is phi of E comma phi of A, right? That is E comma B. And this does not belong to my H. Okay. So therefore P of H. Therefore the statement is false because we had a normal subgroup of G. Under automorphism, its image did not land in what I can say. Its image did not land in my original group. Okay, so therefore A is false. Okay. And now the statement B, that ZG is a characteristic subgroup of G or not. Okay. And but also note that what statement 4 says here, that every characteristic subgroup G is a normal subgroup of G. So this is kind of converse of the previous statement here. The previous statement means the statement A here. What statement A said that every normal subgroup is a characteristic subgroup of G. And what this statement says is that every characteristic subgroup of G is a normal subgroup of G. That's what it is asking. And here the statement B says that ZG is characteristic subgroup of G. And so let us wait. So if we prove this last statement that every subgroup of every characteristic subgroup of G is a normal subgroup, then B will always hold, right? Because ZG is always a normal subgroup. Okay, so what we will do is we will try to prove D, that every characteristic subgroup is a normal subgroup. and then we will try to go to the B part. Okay, so let us try to prove the D part first. Wait, I think what I said is not correct, but let us try to prove D part first. If we correct. Okay, so what I said is not true actually. What the statement 4 says that every characteristic subgroup of G is a normal subgroup. What I said was that ZG is a normal subgroup, but again we can't say that it can be a characteristic subgroup of G. We will prove that, okay? But first of all, let us try to prove the D part, that every characteristic subgroup of G is normal subgroup. So first of all, note that for every G in G, we have this, right? This automorphism such that X we can say into Gx G inverse. And this Tg is automorphism for every G in G. You can check this. For every G in G, this Tg will form an automorphism. Please check. This you can check. And it's easy to check, okay? You can obtain the inverse and so on. That's not a problem here. But what we can now say that it is a characteristic subgroup. Okay, so if something is a characteristic subgroup, then image of that element must lie inside that group is. So if H is a characteristic subgroup of G, then this Tg of H must lie inside H, right? But what is Tg of H? It is GH G inverse, must lie in H. And for each G, Tg belongs to, let me write this. For each G in G, Tg belongs to odd G. Okay, so this must hold for every G. So for all, so for all G in G. So these imply GH G inverse belongs to G for all G in G. And then this will imply that my H is a normal subgroup of G by definition. So the catch here is that all the elements, all the this all the maps of this kind TG are automorphisms. They give automorphisms on group G. And in case of abelian group, this TG actually becomes identity isomorphism or automorphism. So the catch here was just to checking that this TG of this kind is actually automorphism. Please check that this is injective, surjective, bijective, and so on. Okay, you can check this. We would and the yeah, and the last part, yeah, this one. So this one is true. Okay, we just proved this. And now we will go to this B part, that ZG is a characteristic subgroup of G. We will use one result which we proved in earlier lectures in order to prove this. Note that ZG, we can prove that this ZG is actually generated by this XY, X inverse, Y inverse, such that X comma Y belongs to G. Okay, we proved this. If you remember, we actually proved this, that ZG, the center of G is all those A in G, such that for all X in G, AX is equal to GXA. And one can prove that this is actually equal to this set. I mean, both statements are different. Here, I am just characterizing what ZG is. And here, I am saying that if I want to obtain ZG, it is generated by elements of this sort. So if wait, yes, so just a second. Then if I have T, then if I prove that for every element of this kind, my image will also be generated by elements of this kind, then it will prove that my ZG is actually sitting inside its image. So what we need to show that that this T of ZG is inside ZG. So if I show that, I mean, it will follow from the definition of T itself. So since elements of ZG are generated by elements of this form, then what is this? A will be some, then T of ZG will be, sorry, for A belongs to ZG, this A is some product of Xi, Yi, X inverse, so Xi inverse, Yi inverse, right? And I belongs to some lambda, doesn't matter. Then this T of A will be what? This T of A will be this product, let me just write I, Xi, Yi, Xi inverse, Yi inverse. Okay, and then this will be what? My T of Xi, Yi, Xi inverse, Yi inverse. And this is product I, T of Xi, T of Yi, T of Xi inverse, T of Yi inverse. And this is what? This is product of I, some, this is T of Xi, T of yi, T of xi whole inverse, and T of yi whole inverse. And since T is automorphism, T of xi inverse and this again belongs to Z of G, if you notice. Because here I have, this is product over I, okay? This is again product of elements of this kind. Xy, X inverse, Y inverse. And here the image which I have here, and we are again in G. This again belongs to, each of this element belongs to U, which we have here. Let us call this set U. U is equal to this set, and ZG is generated by this U. So the image again is element of the products of these UIs. So therefore this T of A belongs to this U again, belongs to this ideal generated by U, which is ZG. Therefore for A belongs to ZG, I have T of A belongs to ZG. Okay, therefore ZG, and this is true for any given linear transformation T. Therefore ZG is characteristic subgroup of G. You can, I hope you understood this. This followed from the definition of ZG itself. And we started with the product. A will be some product of elements of U. And we just obtained this from the, this was a trivial or routine check that ZG is a characteristic subgroup for every G. And so that is ZG will, image of ZG will always land in the image of ZG in any group G. And which part is now left? The C part. ZG, this one is true. And the C part is also true here. Okay. That if G is a cyclic, then every subgroup of G is cyclic subgroup. Sorry, every subgroup of G is a characteristic subgroup of G. Can anyone give me a quick argument here? Note that if G is a cyclic, then G is generated by something like this. And H is A power M, where A greater than equal to M. And for any given T, since T is an automorphism, T of A power M will be what? T of A power M. And what I can say here, I need to show that it is again some power of M. And you can check that this actually happens. We will try to prove that since we are running out of time. This H is A power M, and we have to do this with the order. That order of H power A will be E, and so for every T power T A power M will be T of A power M, and G is cyclic. So using the order of A, and this M will be the list such that A power M belongs to this H. We can obtain that every subgroup of cyclic is a characteristic subgroup. Okay, you can check this. If not, then we will definitely discuss this in our next session. Okay. Is there any doubt other than this? I mean, this we need to check. We need to prove. Uh, I will upload the solution for this last part in the notes. But apart from that, any doubts here about whatever we discussed so far? Since we are out of time, uh, I will upload the solution for this in the notes and submit the notes. And if not, then we can end the session here. Okay, no doubts. Thanks.